Alright everybody, here's the lesson for 5.1, which is about exponential functions. So here's the basic format for an exponential function. They look something like y equals a times b to the x. Mainly now the variable x is an exponent, so that's really the difference here. Okay, now there are some restrictions that you guys should get familiar with. One of those restrictions is that this base for the exponent x can never be 0, because if it is 0, then this whole thing is just going to be 0. And we don't care about y equals 0 if we're talking about an exponential function. For that same reason, it can't equal 1, okay? Because then we just have a times 1, basically, and we don't get an exponential function that way. And also, the base has to be positive. Okay, and the reason for that is because if, let's say for instance, we have y equals, let's make it 5. 5, and let's make it negative 1 to the x. And then what's going to happen is that when you start plugging in numbers for x, like x equals 0, okay, that's fine. Negative 1 to the 0 is 1, you get 5. When you plug in negative 1 to the 1, you get that times 5, which is negative 5. When you plug in 2, negative 1 squared is positive 1 times 5 is 5. So basically what's going to happen is this function kind of jumps back and forth between 5 and negative 5. But then there's several places where this function doesn't make any sense. For instance, right here at x equals 1/2. If you plug in a half into this exponent, that's the same as square rooting negative 1, which you can't even do. So this is just a weird thing that we're not even going to worry about. Okay, so for these reasons, the base of the exponential function always has to be 0, or can never be 0, sorry, can never be 1, and also has to be positive. Okay, so let's just go through some examples of how to graph these so that you guys can see how these things look. Let's start with y equals 2 times 3 to the x. Let's say you wanted to graph that. Okay, so I'm going to just do this the old-fashioned way until we start to kind of see what the patterns are and what these things look like. So I'm going to make a table, and I'm going to plug in x equals negative 2 into the exponent for x here. Let's see what I get. 2 times 3 to the negative 2 is the same as 2 times 1 over 9, so I get 2/9. If I do 2 times 3 to the minus 1, you get 2 times 1/3, which is 2/3. Plug in 0. 2 times 3 to the 0 is 2 times 1, which is 2. 2 times 3 to the 1 is 2 times 3, which is 6. And then 2 times 3 squared is the same as 2 times 9, which is 18. Okay, so here are the values. And let's just kind of look at the graph. So at x equals negative 2, the graph is just above the x-axis at 2/9. At negative 1, it's a little closer to 1 at 2/3. At 0, now y is 2. At x equals 1, the graph is at 6, so 1, 2, 3, 4, 5, 6. Now we're all the way up here. And if I graph 2, that's going to be way up there at 18. So you guys can kind of see that the graph of the exponential function looks something like this. Okay, a couple things that we should notice here. This graph, no matter what negative number I plug in, will never cross this x-axis. Okay, if I plug in a negative number, like negative 10, all that does is make this 3 to the minus 10, which then makes it a really tiny fraction. So this keeps getting closer and closer to 0 as you go to the left, but never crosses the y equals 0 line. Okay, so for that reason, we actually have a horizontal asymptote at y equals 0. Okay, so y equals 0 is an asymptote for the graph. There's no vertical asymptote. It may look like there's one right here, but you can keep plugging in numbers for x. It just goes up really, really far. Okay. Let's see, the domain for this graph, since you can plug in anything for x in the negatives, you can plug in 0, you can plug in any positive number, the domain is always all real numbers, or negative infinity to infinity. The range, since this is never going to touch 0 or go below 0, we say it's from 0, and then the highest value for y looks like infinity. Okay, so from negative infinity to infinity is the domain, and then for the range, again, we go from bottom up. The lowest value is almost 0, so that's why we have y equals 0, and then goes up towards infinity. So here's our domain, here's our range, horizontal asymptote, and you get a pretty good idea of what this graph looks like. Okay, we'll do one more example. Let's say we have y equals negative 3 times 1/2 to the x. So same idea. Do this the old-fashioned way. And you will have to kind of graph some of these without a calculator for your assessments. So make sure that you can do this. So make a table negative 2 to 2. And we'll do the same thing. Plug in these x values and see what the graph looks like. So if I plug in negative 2, it's negative 3 times 1/2 to the minus 2, which becomes negative 3. And again, a negative exponent just means the reciprocal. So 2 over 1, and now we can make the exponent positive. 2 squared is 4 times negative 3 is negative 12. Don't forget to follow the order of operations. You cannot multiply this number times 1/2 first and then go to the negative 2. Do the exponent part first and then multiply by negative 3 at the end. Okay, so doing that all the way down, 3 times 1/2 to the minus 1, or I'm sorry, negative 3 times 1/2 to the minus 1 is negative 3 times 2 to the positive 1. 2 times negative 3 is negative 6. 1/2 to the 0 is just 1. Negative 3 times 1 is negative 3. Negative 3, and then we do 1/2 to the 1 is negative 3 times 1/2. So negative 3 halves, or negative 1.5. Negative 3 times 1/2 to the 2. You get negative 3, and then 1/2 squared is 1/4. Oop. Let me make sure I have these exponents in there. That's good, that's good. Oh no, we're all right. Sorry, I already kind of figured these out. Ignore what I just did, sorry. Okay, so anyway, these are the values that we get for the graph. Let's go ahead and graph it. So at negative 2, we're all the way down at, let's say this is negative 12. At negative 1, we're at negative 6. At 0, we're at negative 3. At 1, we're at negative 1.5. At 2, we're at negative 0.75. And I think you guys see the idea here. So here's what this graph looks like. Kind of the opposite of what this graph looked like. Well, actually, there's a couple things that are happening. Okay, in general, if this base is bigger than 1, then this graph is going to get big really quick. Okay, if this base is less than 1, like 1/2, then what's going to happen is this graph is going to start to decrease, and it's going to look something like this. But if there's a negative in front, like this one here, so if you think about a decreasing graph that looks something like that, you know from experience from chapter 3 actually, that a negative in front of the function is going to reflect it over the x-axis. So now it looks something like that. Okay? And here's your asymptote again, y equals 0. The domain, if you look again, seems to be all real numbers. There's no x value that will never not work. The range, since it got reflected over the x-axis, now instead of 0 to infinity, it's negative infinity to 0. Okay? Now, here are some general observations. Hopefully you've made these on your own. The domain for exponential functions is always negative infinity to infinity. The range depends on the horizontal asymptote. Okay? So for instance, if we have y equals, let's say a to the bx, and then we have this plus c value at the end. Okay? This value is going to be the value of the horizontal asymptote, because you know that if there's nothing here, the asymptote is going to be y equals 0. But if you add something at the end, that's going to shift the asymptote up. If you subtract something, it's going to shift it down. So depending on what this horizontal asymptote is, that's how you're going to figure out the range. Okay? So depending on whether this is a negative graph or a positive graph, you might be from negative infinity to c, or the other option is from c to infinity. So just real quickly, here's what I mean by that. Like if we have y equals 2 to the x plus 1, this tells me that the horizontal asymptote is 1. And since this is just a regular positive exponential graph, it's going to look something like this. So the domain is all real numbers, and the range is from 1 to infinity, because the asymptote, which used to be at y equals 0, got shifted up to y equals 1 because we added 1 to the exponential function. Okay, the other option is maybe there's a negative here. If there's a negative here, let's do that in a different color, then all that's going to do is just flip the graph over. So now it looks something like this. And now the range would have been from negative infinity to 1. Okay, so this number at the end determines where the asymptote is, and then depending on what your graph is doing, that's going to change the range. Okay, so that's how to graph the exponential functions. Now there's a bunch of algebraic things that you should be able to do in this chapter, so I'll go through those real quick. Okay. One is you should be able to simplify exponential expressions. And really nothing different than what you've done before, but they're just going to look a little weirder, that's all. So for instance, if we have something like this, 7 to the root 5, and that's to the root 5, you know from before that you just multiply your exponents. So you could say that this is 7 to the root 5 times 5, which is just 5, which is, if you have a calculator, 16,807. Okay, so it might start out looking kind of different, but you still do the same rules. You multiply in this case, so this is one example. We can do one other quick one. Let's say I have something like 9 to the pi minus 3 over 2 divided by 9 to the pi minus 5 root 2. So here's another another time when you still do the same rules, but it looks a little goofy. Here we're dividing a number that's the same base. When you divide, you subtract your exponents. So you're going to do 9, and then the exponent will be whatever you get when you subtract the exponent. So you're going to do pi minus 3 root 2, and then subtract pi minus 5 root 2. If you see here, the pi minus pi will cancel. Negative 3 root 2 minus negative 5 root 2 is the same as negative 3 root 2 plus 5 root 2, which you can combine to get 2 root 2. Okay, so I would accept this answer on a quiz or a test. You could also say that this is the same as 9 squared to the root 2 using the exponential property that you can multiply these exponents to get this answer right here. So you could also say that this is 81 to the root 2. So either 81 to the root 2 or 9 to the 2 root 2 would be okay answers with me. Okay? So that's some basic simplifying examples. You should also be able to solve exponential equations, which is a big deal in this unit. That's where logarithms are going to come in, but not yet. Right now we'll be able to do these without using logs, and it's not very difficult. For example, let's say we have 10 to the x minus 5 equals 1,000 to the 4x minus 1. If your goal is to figure out what x is here, the only way that we can do that is to say that since 1,000 is 10 cubed, and then if I simplify the right-hand side, you get 10 times, if you distribute here, 12x minus 3. So we have 10 to the x minus 5 equals 10 to the 12x minus 3. If you can turn this exponential equation that starts out with different bases into an equation that's exactly the same base, if this is a base 10 and this is base 10, in order for these two things to be equal, well then x minus 5 has to equal 12x minus 3. Otherwise this equation doesn't work. Okay, so if we solve, we can add x or subtract x to make this 12 into an 11x. We could add the 3 to make negative 2 on the left, and you get that x has to be negative 2 over 11. Okay? So just to recap, if you see an exponential equation, you change so that all bases are the same. So make sure all the bases are equal. If this is base 10 and this is something bigger, you can make the 1,000 into base 10. Okay, another quick example. Let's say I have something like 5 times 125 to the x minus 5 equals square root of 5 to the 2x plus 7. Okay, well, base is 5, base is 125. I know that 120, whoops, got ahead of myself there. I know that 125 is the same as 5 cubed. So I'm going to leave the 5 as just 5 to the first. I'm going to change the 125 into 5 cubed. Still, the x minus 5 is outside of this. On the right, the square root of 5 is the same as 5 to the 1/2. A square root is the same as a 1/2 exponent. If this were a cube root, you can do 1/3. If this were a 4th root, you could do 1/4, and so on. Okay, so your first step is to get all the same base. And then you can rewrite the equation as 5 to the 1 times 5 to the 3x minus 15 after you distribute the 3 here. If you distribute the 1/2 on the right-hand side, you get 5 to the x plus 7 over 2. When you're multiplying on the left-hand side, you can add the exponents. So this becomes 3x minus 14 for the new exponent, because you're going to add 1 with 3x minus 15. You combine your like terms. So you get 5 to the 3x minus 14 equals 5 to the x plus 7 over 2. Okay, so this is a little bit more difficult than the previous example, but it all works similarly. Start with a weird equation, but notice that all the bases can be written as base 5. Change it, simplify all the exponents, get it down to where it's 5 to a power equals 5 to a power. And now these two powers, these two exponents, have to be the same, and then that's how you solve the equation. So if you set the exponents equal, subtract x to get 2x, you add 14 to the other side, which is the same as adding 28 over 2 if you do common denominator. That becomes 35 over 2, and then when you divide by 2, your final answer becomes 35 over 4. Okay? Last example, and then we're done for this section. And that is something like this. Let's say I have 2x squared times 5 to the x minus 5x times 5 to the x minus 3 times 5 to the x equals 0. Sorry about that. There it is. This might look challenging, but really it's not. The only thing that's strange about this is that there appears to be this 2x squared, this minus 5x, and minus 3 that we're comfortable looking at, but for some reason there's a 5 to the x in here. Well, notice that the 5 to the x is common to all three terms. Anytime you have a common factor, you can take it out. So if I take out 5 to the x, rewrite it, you get 2x squared minus 5x minus 3 equals 0. So that's your first step. If you see a common exponential factor, you can still factor that out, as goofy as that looks. And then you can keep factoring. If you factor this by trial and error, it's going to be 2x, x. This needs to be 3, that needs to be 1, this needs to be minus, that needs to be plus. And now you just set each one of these equal to 0. So 5 to the x equals 0, 2x plus 1 equals 0, x minus 3 equals 0. Here you got x equals 3. Here you got x equals negative a half. Here, we'll talk about this for 10 seconds. This is an impossible equation. If you remember what the graphs of these exponential functions look like, there is never a time when 5 to the x is going to hit 0 because there's an asymptote at y equals 0. And you can kind of look at it too and say that no matter what exponent you plug in for x, if you plug in positives, this 5 gets larger. If you plug in 5 to the 0, you get 1. If you plug in negative numbers, that doesn't make the answer negative or 0, it just means you do the reciprocal, which is just going to make it smaller but never equal to 0. So you're going to ignore this factor here, but factor the other remaining quadratic and solve like usual. So the two answers for this equation are x equals negative a half and x equals 3. Okay, sorry about the length. I'm going to try to keep these videos to hopefully 15 to 20 minutes at most. I went a little long today, but there was a lot of stuff in this introductory section. So I'll see you guys in class. Bye-bye.